Okay, hello everyone, and start by apologizing for this clickbait title, but I had to say something to get people to the talk. So, how many here are security people? I can see quite a few of you here. We're working with security, so this is not for you. So sorry.
Okay, thanks.
This is a little bit about giving introduction of things that could go wrong. I mean, you quite often hear that it's hard to write secure software and so on. So we just wanted to raise some things that could be, good to know. So I'm Joakim Bech, I'm the lead for security working group, and I have Ard here also, who will fill in a little bit. He's my sidekick today. So the agenda, why are we having this talk? Some terminology, a little bit about the introduction to encryption modes and IV, and we have to deal with random number generators also, touch that, and finally we have the side channel attacks. And as I said, we would like to have this as some kind of eye-opener for people who are not working with secure software on a daily basis, so you kind of know what are the challenges. And we also want to spread some knowledge about well-known pitfalls. And as you know, with Spectre and Meltdown, the side channel attacks has been quite a hot topic lately also. And Ard, do you have a kind of a view on how this could be done also?
Yeah, so this is really what I'd like to call the circles of enlightenment, or circles of hell, perhaps. We all started programming, wrote our first program at some point, and we all started at something what you call like happy flow. You write your code, you only consider what the intended code flow is. You only consider what you want to be done, and you have no consideration whatsoever what could go wrong. You basically move the turtle around, and So then there's the first level where you really start considering, okay, if I call this function, this is what I hope it returns, but it could return errors, it could do other things that I don't fully expect, which I call level 1. The next level is where if you get more into secure programming, systems programming, that kind of stuff, where you really should be very aware of, okay, if I write this in C and this ends up on the stack, this is going to look like this in memory. If I make it static, or if I do make it const, is it actually const from the view of the compiler? Is it actually const from the view of the linker? So being aware of how your code is projected onto the machine, basically. So for if you go more into the topics that Joakim is going to address, then there's an additional level where you should be really aware about that you're running on actual hardware. You're running on something which is basically a big analog crystal that has been abstracted into a logical digital model, but there are other things like how long it takes to do a certain operation, or whether someone's poking at the clock line, and what effect that has on the execution of your code. The last line, so about hero attacks. So you have to, if you build like a secure system, a hardened system, a tamper-proof system, you should distinguish between being resilient to hardware hacks that allow you to exploit your own system and make it do things you don't want it to, and hero attack is where you hack a system, learn something from it that you can apply to other systems without even having to hack them, and that's a very
you basically use a sacrificial device to
yes.
attack, and then you can use
So typically, if you need to solder wires to something, open it up to hack it in the first place, and you have to do it to every system to achieve that, that's usually not such a big deal. If you can have to hack a system only once, and you can apply it to every system via a network attack, that is usually a big deal. So that's something to be aware of.
Okay, thanks. So let's jump into the different modes we have. Oh, sorry, we had this one first. So this terminology. So you often see these 4 words when you're reading about secure software. So we have authentication, integrity, and confidentiality, and non-repudiation. So authentication, that's when you verify your identity. So you tell someone who you are. And we can do that in the physical world by showing your driving license, but in the computer world we usually do it by login credentials, passwords, PIN codes, etc. Integrity is that you want to ensure that someone hasn't tampered with your data. So that's where we typically put signatures, macking and so on software. Confidentiality is what we refer to as encryption. So you scramble the information so no one else can just read it as a plain text. And finally, non-repudiation, that is that you are accountable of something you have done. You can't really deny it, but you have made a signature with either digitally or just by signing with a pen. So this takes us to the different modes you're using when you're working with encryption. And ECB is the most simple one, and it's barely ever used. But I wanted to still show it here because you hear quite often that you shouldn't use it. It could be good to know why. So it's malleable, which means that you can influence it quite easily. You can basically do whatever you like with the plain text and the ciphertext when you go in the other direction. Another property here is that each block is individually decrypted, so you have no connection between the different blocks, which you have in other modes that we will see. So you will always get the same ciphertext with a given key. And all of you have probably seen this image with the penguin, which, yeah, don't have to say more. So what could an attacker do, in this case a man in the middle? So we have a simple bank transaction here, and this could be the format of the packet. We have a sender, receiver, and an amount. And if David would have been the man in the middle here, for example, we shouldn't trust him. Then he could, for example, randomly change the amount by just XORing in something in the encryption in the encrypted data. He could replay a packet, so you would get the same information again. He could even change the receiver, so David would end up getting all the money instead of Ard. And these types of attacks. So this is what you need to be aware of. So that takes us to the other modes, and quite often you hear about CBC and CTR. And these are the types of mode that you, in almost all cases, should use if you have some kind of data size greater than a block size. So barely, don't think about ECB. Forget about it. CBC is a mode that you can't run it in parallel when you're doing encryption, but you can encryption, but you can do it when you run the decryption. But this mode also needs padding, so it's subject to something called a padding oracle. And with that, you can, during the encryption phase, I know I don't have the encryption image here, but it's the reversed way, then you can basically modify the ciphertext by XORing in information, and when you do that, you can find a good padding value, and by doing that you can figure out the plain text. If we go into CTR, which behaves as a stream cipher, then you're subject to something called a two-time pad, which means that you can see on this image here, you basically have the key and the plain text, which is XORed, so you get a ciphertext. So if you reuse the same key more than once, then you can XOR the two ciphertexts together, which basically will cancel out the key, so you will end up with a plain text that's been XORed together. And using something called creep drag, you can figure out what the plain text was, and even the key. Anything you would like to add?
think that the last part was a little bit too quick for me. I don't know.
Okay.
Not the key, the gamma. The whole code stream
Which one?
in the CTR mode.
CTR. So you can see here you have, if you forget about this part, because this is what makes this secure also, but if we only look at the key here, and you have the plain text, you have an XOR operation, and you get the ciphertext. So if you have used the same key twice, the XOR, the ciphertext here is basically key XOR plain text. So if you take that with another ciphertext, you get M1, M2, key 1, key 2, XOR together, so the key cancels out. So that's the issue.
Question about not, sorry, to be precise, the key not about using the key twice, but about using the initial init vector twice, because the key is can be stable for different encryptions, but yeah.
You're right, we're coming to that.
Okay, sorry. Sorry.
So, but in general, I mean, when you need authentication, which we'll also come to later, you use some other modes. I will mention it.
It's actually quite interesting because quite recently Google engineers who were concerned about full disk encryption on the older Android systems that don't have the AES instruction, they tried to upstream an alternative version based on CHA-20, which is a stream cipher, for doing block encryption. And when you're doing block encryption, the IV is basically derived from the sector, and the sector never changes. The sector number is always the same. And their argument was that, okay, so we shouldn't actually be using a stream cipher, because you could XOR different generations of those blocks together and you could perform this attack.
Yeah.
But because their primary the primary attack they were defending against was having the device seized and having forensics trying to reverse the information or decrypt the information. And they said, so usually you will only have one generation of the block. Of course, that's not entirely true with flash file systems, either in the ware leveling layers and in the software layers that you have. There might actually be different generations of the same block accessible to whoever performing the attack, which is why they ended up dropping the patches, withdrawing the patches, because, well, it's not secure at all, and it gives an appearance of security, but it's really false sense of security. Yeah, exactly.
Thank you, Art. So then we have something called IV. So this was the first time I saw this. It was really strange. You have to have some kind of random value, and you don't even have to protect it. But the thing is that you need to have something that gets the encryption going, and that's what it's used for. And as I said, it doesn't have to be secret. It could be a timestamp, it could be a random number, and it could be a sequence of numbers, and that could even be more secure. But in that case, you need to keep track so you don't reuse the same IV again. So that's another challenge. But the key message here is that you should not reuse the same IV for a given key and message, because then you're subject to what we just talked about. All right. That leads us into the, now we said that we have the encryption and we have some better modes that are chained together. Then we need to also have the authentication and integrity protection. So which order should we do it? Should we do encrypt then MAC, or MAC then encrypt? Encrypt then MAC. Who thinks that's the correct one? Hand up. 1, 2. So the rest of you think MAC then encrypt. So only 2.
I would look it up first. No, that's an answer. I can never remember which.
So Ashu and you can take some candy because you were right. So you should always encrypt then MAC, because it's the same. Otherwise, you're kind of modifying information that you shouldn't be able to do. Okay? Random number generators. So here we're talking about a string of numbers that should be random. And you have 3 different variants here. TRNG, PRNG, and CSPRNG. TRNG is true random number generator. You can use it hardware to gather noise, clock, jitter. I even have a random number generator here. It's a coin. It's perfect random number generator. Pseudo random number generator, that is typically what you find in C, and you shouldn't use that. And the main reason for that is that you use the random sequence given by an initial seed. So if you use the same seed again, you will get the same random sequence, and that's not good for crypto. So you need a CSPRNG. The requirement for CSPRNG is that it should be unpredictable, and there are ways to tweak the PRNG so it's possible to get this property. And without true randomness, you can't really get reliable security.
So I think the bold and underline is missing where it says, so the middle part, the rand in C, that's, you should never consider using that for anything remotely related to security. Yeah. It's nice to, for some numerical algorithms or other things where you need some kind of random input, but for security it's completely inappropriate.
Yeah. So Arnd, do you have more candy?
Yes.
Time again?
Big one or small one?
So this silly trivial example here, there are some things that could be improved. So any obviously spot here? Ashu?
Mem compare.
Mem compare? Well, that's one right. Someone else? Mark?
It's non-constant time.
Right. Timing attack? Someone else? So everyone, oh, see?
Sticking around in memory.
Pardon?
It's sticking around in memory, they're super secret.
Yes, yes, that's right. Something else? Do you think this is nice? No verification? Input parameter? So.
You deserve a sweet or so.
So you basically cover it, but we also have the glitching attack, and I will mention that too. So the timing attack, the idea here is that you measure the time it takes to do some kind of operation. And for Spectral Meltdown, you were measuring the time it took to access the cache. That's how that was used. Mem compare, if you ever think about doing that for comparing passwords, forget about it. You should not use it, not standard mem compare. What's this? The reason for this with mem compare is that if you look at the implementation, it compares byte by byte. If it's wrong, it will return immediately. If it's correct, it will traverse through all the bytes. So it will take more time verifying the correct password. So it's easy to brute force. Table-based AES. Do you want to say something about it? Or?
Yeah. So the problem with table-based AES is that the tables are fairly large. So you have typically like 16K worth of lookup tables that are used to basically accelerate the algorithm when you have in a C-based implementation. And because the size of the tables, it's quite easy to measure cache, caching effects it has. So you should have a constant time implementation instead, which may still be, or if the tables are much smaller, you can mitigate it a bit, or ideally use instruction-based or SIMD-based algorithms that are don't depend on tables at all.
And the final example here is something that actually was in CV in Opti 2 years ago or something. We used this left to right implementation when doing the RSA operations. And what you're doing is that you're working on the exponent of the key. And the trick to speed things up with this easy implementation, L2R, left to right, is that you square when the bit is 0, and you square and multiply when it's 1. So if you can measure this time, you can basically just read out the private key. So here you should strive for having this kind of balanced operation. So if you need to compare something that needs security, you should make sure that it takes the same amount of time, regardless if it's the correct value or incorrect value. But compilers can be an issue. So they are too helpful to try to make the best out of this and speed it up and so on. So it could be important to check the output from the compiler here also. Next side channel attack is about measuring the power. It's related. So when you're running something on a device, you will have some kind of distinct pattern from, basically during runtime. If you can measure different amount of power, then you can figure out the same kind of information as I just showed on the previous slide. So in the square and multiply example, you could use that also as a timing attack to just visualize it. You can also use it to find out intermediate states in AES to recover the key. And you can figure out simple things like where is the if-else if you need to do a glitching attack. So this is quite powerful, and especially the DPA can make things that look quite complicated when just running it once. It can basically cancel it out with some statistics involved. So glitching attack, 2 ways. You can inject extra clock signals, like in the normal flow you just brute force something else in, and it will make the CPU misbehave. And if you don't have an external clock, you can ground VCC for a few nanoseconds and you would get the same kind of behavior. This is weirdly written. The logic is very strange here. But return 0 means that it's not granted and 1 means granted. So if memcompare returns something not 0, then we have granted access. So if we glitch during memcompare, it's a high likelihood that memcompare will return something not 0. So even though we had the incorrect password, it will still return true. Okay.
Yeah, so the issue here is basically how you encode the value, right? So there's only one of all the possible values of this variable, that means access denied, and every other value means access granted. So you have to encode your security states. This ties into the level 4 I mentioned earlier, where you encode values in a way that it's the likelihood that some attack will result in access being denied. So the likelihood is higher to end up being denied rather than being granted under these kinds of attacks.
And the takeaway here is that with this kind of attacks, glitching attacks, is that if you read the source code, everything looks perfectly fine logically. I mean, every sequence looks good, but if you inject a glitching attack, well, the if case is just ignored. You just end up in the code anyway, inside if. And there's no real good software mitigations against it. There are some tricks you can play, but this is a hard thing.
So, but from a software point of view, you just have to think some bits could be flipped at random.
Yeah.
Okay.
Yeah.
So it's just the result of the memcmp can be not written to the end value. And so, for example, if memcmp returns true, but then you insert a power glitch during writing of this 0 value to the register, it can end up being not written to the proper register or proper memory location. And then even at this point, even with the wrong password, the login branch will be still 1. Sorry.
Yeah.
And to point out the previous slide, the point made in the previous slide is you may say, oh, well, let's fix the logic, start it out as 0,
put a not in front of the mem compare and set it to 1, and the compiler might not even generate different code when you do that,
Right.
Yeah.
Yeah.
because it's trying to be helpful.
Exactly. So should we consider toolchain engineers as evil people? So I'm about to wrap this up now. So this is what you can use, like the instructions from the architecture. So these are the instructions to measure the time. As you know, with JTAG you can do basically anything. Oscilloscope, logical analyzers could be used to measure the time and current. Or you could use special tools dedicated for this. So this is a pretty cheap side channel attack tool that you can use. It costs around $300 or something. And this is the final slide I have. So we've just scratched the surface here. I mean, we could probably talk many hours about this, but these are 2 really good courses and lectures. Serious. So if you want to know more about things like this and you're working with secure software, then I really encourage that you have a look at these 2 links. And that was everything from me. I think we're about to run out of time, I guess, so maybe 1 or 2 questions. John, can we have 1 or 2 questions? You're next. Ashu?
Yeah, so one of the points you raised is about the tool chain.
Grab the mic.
The perennial problem with the tool chain and the kind of code it generates, which tries to be very helpful. Is there some tooling which helps, which can be used, or some sort of scripting that can be used to at least detect this kind of problems in the final binary output, and then do something about it later on? So I think the first question would be, is there something that allows us to do the detection? And the second question is, how do we fix it?
Yeah, I should probably know the answer, but I don't really know, to be honest. But I think you can use, in some cases, you can use like volatile to make sure that the compiler doesn't do anything.
Why don't you start by turning off all optimizations? Start at 0, right?
Sounds like a good idea.
Yeah, so yeah, that's fine.
Yeah.
Override everything.
Kill the performance and then
Yeah, but I think
You're using a tool that optimizes and you want it to not optimize. You're
Right.
using a tool.
So on that note, Ray, what they do when they're manufacturing a lot of SoCs now is there are third-party consulting companies that will do differential power analysis attacks against it, and they'll tell you, you screwed up here, you screwed up here, you screwed up here. So we can do that, we can do constant time operations, lots of changes we can make, but fundamentally I think the point is to draw awareness and tell people as you're building chips, there's a reason you pay those consultants to tear it apart, because you can detect a memory bit flip in some code somewhere, but who knows, it's not doing bit flips in your cache or something else. I mean, this is one example, but really you've got to get people to tear it apart and actually find the problems.
so. Anyone else?
Basically, I would add another source to your last slide, being the applied cryptography by Neil Ferguson and Schneider. Yeah, sorry. I would add another source to your last slide, the applied cryptography by Neil Ferguson, because okay, it's doing the right thing to me, the mic. Because it's really a really good source for the recipes, what you should do and what you should not do, not from the theoretical perspective point of view like the Coursera's course, but just from the recipes point of view. If you are just an engineer, just do this, this and this. It is not up to date, unfortunately, but it's still a good thing too.
Okay, well, that wraps it up. So thanks everyone for attending.